Rivers have flowed backwards across the face of our planet. This is not a theory, but a fact written in stone. The mighty Amazon River once poured into the Pacific Ocean, a complete reversal of its current path. This video will give you a completely new understanding of how our world works, revealing the invisible forces that literally redraw the map. We will uncover how entire mountain ranges can act like dams, and why the fossils of a fish can tell a story of a continent tearing apart. How could something as constant as a river's flow simply turn around? Our planet's surface is a deceptively calm mask over a world of immense, restless energy. Think of the ground beneath your feet not as solid and permanent, but as the topmost piece of a vast, moving puzzle. These puzzle pieces are the tectonic plates, colossal slabs of rock that form the Earth's crust. They float on a layer of hot, flowing rock called the mantle, which moves with the slow, powerful churn of a pot of soup on a low boil. This constant, gradual motion is the engine of our world. Plates drift apart, creating brand new ocean floor in the gaps. They collide, crumpling their edges into towering mountain ranges that scrape the sky. They also slide past one another, building up immense pressure that is released in sudden, violent earthquakes. This grand planetary process is known as plate tectonics. It is the ultimate continental force, the master architect that redraws the world map over millions of years. Every mountain range, every ocean basin, every coastline is a temporary feature in this endless dance. And it is this slow, relentless shifting of the land itself that changes the fundamental tilt of the continents, the very angle of the ground that every river must follow. When a continent rises or falls, even by a tiny amount, it changes everything for the rivers that flow upon it. They are simply following the new path of least resistance, a path carved not by water, but by the unimaginable forces deep within the Earth. 300 million years ago, the entire Earth wore a single face of land. This was Pangea, a supercontinent, a colossal jigsaw puzzle where every piece we recognize today was locked together. A single world-spanning ocean lapped at its shores, but this unity was not destined to last. The same deep Earth forces that keep the plates in motion began to pull this giant apart. It was not a clean break, but a slow, violent ripping that sent continents drifting on journeys that continue to this very day. As these massive landmasses tore away from each other, their edges crumpled and collided, birthing new mountain ranges that would act as continental dividers for millions of years. In their wake, vast lowland basins sank and filled with sediment. This global reorganization was a complete overhaul of the planet's plumbing. It erased ancient river systems and carved out entirely new pathways for water. The fragmentation of a supercontinent is the ultimate catalyst, the dramatic first act that sets the stage for every river reversal to come. The world's drainage map was literally torn up and redrawn from scratch. The Amazon River today is a titan of the Atlantic, pouring a staggering volume of fresh water into the ocean. Yet this has not always been its path. For a period spanning tens of millions of years, this colossal river system did the exact opposite. It flowed west, carrying its waters across the continent to empty into the Pacific. This is not a guess, but a conclusion written in stone. Geologists have deciphered this ancient story from the land itself. They find the evidence in thick layers of sedimentary rock, the compressed remains of mud and sand that were once carried by the current. They see it in the fossilized channels of long-vanished waterways, all pointing like arrows toward the Pacific. This was the original Amazon, a river flowing in a world we would scarcely recognize. Its westward journey was dictated by a simple, powerful fact. the land itself tilted in that direction. Before the great rise of the Andes Mountains, a vast elevated plain stretched across what is now South America. This highland, known as the Purus Arch, created a gentle but definitive slope toward the Pacific. For eons, every drop of rain that fell in the continent's heart had no other choice. It followed gravity's pull, flowing west and gathering into the mighty river that carved its way to the sea. The entire drainage of an entire continent was oriented in one direction, a testament to the power of the land's original shape. Then came the Great Wall. The slow, grinding collision between the Nazca Plate and the South American Plate began to violently reshape the western edge of the continent. One plate was forced to dive beneath the other in a process called subduction, a geological act of immense force. This was not a gentle nudge. It was a colossal crumpling of the Earth's crust, a buckling that thrust the Andes Mountains toward the sky. This new mountain range did not just appear as a few scattered peaks. It grew into a continuous, unbroken barrier, a towering wall of rock that stretched for thousands of miles. For the rivers that had flowed westward for eons, this was a catastrophe. Their ancient, established paths to the Pacific Ocean were suddenly and permanently blocked. Imagine a river meeting a brand new dam that is hundreds of miles long and several miles high. There is no going over it, there is no going around it. The water has no choice but to stop, and so the rivers stopped. Their waters could no longer reach the sea, and they began to pool behind this immense natural barrier. What was once a landscape of flowing rivers became a series of vast, trapped inland seas. These were not permanent features, however. They were giant bathtubs with no plugs, slowly filling up. Water always finds a way. With the western exit sealed shut, the only direction left to go was east. The pooled waters began to spill over the lowest points in the landscape, carving brand new channels that led away from the mountains, not toward them. This was a continental-scale act of river piracy, where the Andes Mountains literally stole an entire watershed from the Pacific Ocean and gifted it to the Atlantic. The relentless millimeter-by-millimeter uplift of the peaks did not just create a beautiful mountain range, it actively rewrote the fundamental plumbing of South America, proving that mountains are not passive features on a map. They are powerful, dynamic forces that can change the flow of a continent. So how can we be so certain of this ancient river's forgotten path? The evidence is not hidden in old maps or legends, but locked within the very ground the modern Amazon flows across. Geologists become detectives of deep time, reading the story written in stone. They drill deep into the vast Amazon basin, extracting core samples that are like pages from a planetary history book. These pages are layers of sedimentary rock, the compacted and hardened remains of mud, sand, and silt that were once carried by flowing water, and within these layers they find a geological contradiction. The mineral composition of these ancient sediments does not match the local bedrock of the eastern Amazon. Instead, they contain minerals like andesite and specific types of garnet that have a very distinct fingerprint. These minerals could only have been forged one place, in the fiery, high-pressure womb of the rising Andes Mountains far to the west. Think of it like finding sand from a distant desert on a beach 1,000 miles away. The only way it got there was by a powerful, consistent force carrying it, but the clues do not stop with chemistry. The physical nature of the sediment grains themselves tells a story of force and direction. These are not fine, powdery particles that would settle in a calm lake. They are larger, coarser sands and gravels, and their edges are rounded, not sharp. This specific shape and size is the signature of a long journey in a fast-moving, energetic current. A gentle stream cannot move stones of this size. Only a major river with immense power could pick up this material from the mountains and carry it all the way across the continent. These rocky archives offer incontrovertible proof. They tell us that for millions of years, a mighty river system did indeed flow from the young Andes Mountains eastward across the basin, laying down the very ground that exists today. It is a tangible record of a world turned upside down, or more accurately, a river turned completely around. The story of the river's reversal is also written in bone and tooth. Paleontologists sifting through the ancient layers of the Amazon basin have uncovered a profound biological mystery. They find the fossilized remains of freshwater fish, stingrays, and other aquatic creatures that look strikingly familiar. Yet their closest living relatives are not found in the Amazon today. Instead, these modern cousins swim thousands of miles away, in the isolated river systems that drain the western slopes of the Andes into the Pacific Ocean. This is a monumental piece of biogeographical evidence. It paints a clear picture of a once unified world. For these species to be so closely related, they must have once been part of the same connected family, swimming freely in the same river network when it flowed west. The rising Andes mountain range did more than just block water. It acted like a giant pair of scissors, snipping this continuous aquatic highway into separate, isolated pieces. The fish populations on either side of this new continental divide were suddenly cut off from one another. Trapped in their new, separate worlds, they began to evolve on their own unique paths, becoming the distinct but related species we see today. A fossil is not just a long-dead animal. It is a biological signpost, a permanent marker that points unerringly to the direction of an ancient current. These creatures lived and died in a river that no longer exists, and their very bones testify to its forgotten flow toward a different ocean. A river's power is never just its own. It is a force borrowed from the sky, while the continental forces of plate tectonics build the stage and set the incline. It is the climate that provides the script, dictating the strength and aggression of the water that flows upon it. The same river can be a meandering, gentle stream in one era and a roaring, landscape-carving torrent in the next, all based on the amount of rain falling on its headlands. This climatic influence reveals a crucial mechanism in the rewriting of river pathways, a process known as river capture. Imagine two rivers flowing in parallel valleys, separated only by a narrow strip of high ground. During a prolonged wet period, the more powerful of the two rivers, swollen with relentless rain, begins to cut backwards into the soft rock at its source. This relentless gnawing at its own headwaters, called headward erosion, is like a miner digging a tunnel toward a rival's gold vein. The river extends its reach, digging its channel further and further inland until it finally breaches that narrow divide. In a dramatic geological instant, it punches through the final barrier and steals the water from the neighboring river. The captured stream is suddenly and permanently diverted, its flow now adding to the power of the thief. Its original channel downstream is left a dry, abandoned gorge, a ghost of a river that once was. The opposite scenario is just as decisive. A shift to a drier, more arid climate can weaken a mighty river, reducing its flow to a relative trickle. It becomes sluggish, losing its ability to defend its own territory. A smaller but more consistently fed neighboring river can then become the aggressor, cutting back and capturing the weakened system's headwaters. The timing and success of these hydrological takeovers are never accidents. They are the direct result of a delicate, constant interplay. The tectonic forces create the potential, carving the initial valleys and setting the regional slopes. But it is the climate that provides the opportunity, either by supercharging one river with water or by starving another into vulnerability. This partnership between the deep earth and the open sky is what completes the map, proving that a river's path is a story written not just in rock but in rain. The Mississippi River's quiet dominance over North America was never guaranteed. Before the great interior plains tilted decisively southward, a different aquatic titan ruled the continent's heart. This was the Bell River system, a colossal network of waterways that gathered water from lands as far south as present-day Colorado and Wyoming and channeled it all on a long, northward journey to the Arctic Ocean. Its vast basin connected territories that are now hydrologically separate, a unified river highway flowing in a direction that seems alien to us today. The continental interior, for millions of years, drained toward the pole, not the Gulf of Mexico. The key to this ancient arrangement was the land's subtle, original slope, a gentle declivity northward that guided every raindrop toward a frozen sea. This was the established order, a stable system that persisted for eons. Then, the ground itself began to shift. The slow, persistent uplift of the Rocky Mountains and other western ranges like the Black Hills did more than just create majestic peaks. It acted like a giant hand pressing down on the western edge of the continent. This monumental shove had a cascading effect, subtly warping the landscape for hundreds of miles to the east. The continent's very spine was being bent, creating a new, overarching tilt that favored the south. The Mississippi, once a smaller river confined to the continent's southeastern lowlands, suddenly found itself on the steeper side of this continental seesaw. Its gradient, the slope of its bed, increased dramatically. With a steeper path to the sea, its water flowed faster and with far greater energy. This newfound power transformed the river into an aggressive, land-hungry force. It began a relentless campaign of headward erosion, chewing its way northward, upstream, like a serpent eating its own tail from the mouth backward. One by one, the southernmost tributaries of the Bell River system found their flow interrupted. The mighty Mississippi, with its steeper gradient and superior erosive power, would cut a channel right up to the headwaters of a north-flowing stream. It would then breach the low divide separating them, a process known as stream piracy. In a geological instant, the water from that tributary was captured, its flow stolen and violently reversed to join the southward charge. The Mississippi grew fatter and more powerful with each conquest, its reach extending ever northward. The Bell River, bled dry of its life-giving tributaries, shrank and eventually vanished. Its former channels were left as dry, ghostly scars on the landscape, silent witnesses to a continental-scale robbery. The entire drainage of a vast interior was fundamentally rewritten, not by a single cataclysm, but by the slow, inexorable tilting of the continent itself, a tilt that gave one river the power to consume its ancient rival. But the Earth has a memory of these immense burdens. Long after the titanic ice sheets of the last ice age retreated, the land itself is still rising. This slow, powerful recovery is known as isostatic rebound. Think of the continental crust not as a rigid, unyielding slab, but as a giant, slow-moving mattress floating on a denser layer beneath. When a colossal weight, like an ice sheet 2 miles thick, presses down for thousands of years, the land sinks into the underlying mantle. Then, when the ice finally melts away, that weight is lifted. The land does not spring back instantly. It rises with a profound, deliberate slowness, rebounding over thousands of years, inching upward as the mantle slowly flows back underneath. This is not a historical event confined to textbooks. It is happening right now, a live geological process you can measure. In parts of Canada and Scandinavia, the land is still rising from the removal of ice that vanished over 10,000 years ago. Coastlines are slowly emerging from the sea, and ancient shorelines are now found high and dry far inland. This gradual, continent-scale uplift might seem too slow to matter, but its effects are relentless. By changing the elevation of the land over areas the size of entire countries, isostatic rebound subtly but permanently alters the regional slope, the very tilt that guides every river. A river that has flowed peacefully for millennia might find its gentle gradient reversed as the land rises on one side of its basin. Its current could slow, becoming sluggish and prone to flooding, or its headwaters might be captured by a neighboring river on a steeper slope. It is a persistent planetary fine-tuning of the continental plumbing, a quiet force that works in the background, patiently rewriting the map long after the glaciers are gone. This silent theft of an entire watershed is a geological event of stunning swiftness. River piracy or stream capture is the moment a river's destiny is stolen. It begins with a relentless, patient gnawing. One river, perhaps strengthened by more rainfall or flowing over softer rock, starts to erode its channel not just downward, but also backward, extending its reach ever further inland. This is headward erosion, a slow-motion invasion. The river acts like a miner digging a tunnel toward a rival's treasure, its current constantly chewing away at the rock and soil at its source, inching its way toward the high ground that separates it from a neighboring valley. This dividing line, the drainage divide, is the only thing standing between two independent river systems. It can be a gentle ridge or a towering mountain range. For eons, it maintains the peace, ensuring each river remains in its own territory. But the pirate river does not stop. It continues its backward march, cutting a deeper and deeper gorge until it finally breaches that final barrier. The moment of capture is as decisive as a dam breaking. The water from the neighboring river, which had been flowing peacefully in its own channel for millions of years, is abruptly diverted. It pours over the newly carved gap and plunges into the waiting channel of the pirate. In a single geological instant, the flow of that river, or one of its major tributaries, is completely reversed. Its water is now flowing in the opposite direction, joining a new watershed and heading toward a different ocean. The river that committed the theft grows instantly more powerful, its volume surging with the stolen flow. Meanwhile, the river that was captured is left diminished, its downstream channel becoming a dry, abandoned valley known as a wind gap. This is not a slow continental tilting. It is a violent hydrological hijacking that can rewrite a local map in a blink of the eye. The stage for this drama is set by the deep forces of the Earth. Tectonic uplift can steepen the gradient of one river, giving it the erosive power to become a pirate. A difference in rock hardness can mean one river cuts back far faster than its neighbor. Even a shift in climate can trigger the event by increasing rainfall on one side of the divide and supercharging a river's ability to erode. River piracy is the punctuation mark in the long, slow sentence of continental change, a sudden and permanent theft that proves a river's path is never truly safe. Beneath the rich, black soil of Ohio and Illinois, a lost river sleeps. The Teays River was once a titan of ancient North America, a mighty waterway that carved a deep valley as it flowed north from the Appalachian Highlands. Its path is invisible today, buried not under rock but under the very farmland that now defines the region. This river met its end not from a competing stream, but from an unstoppable wall of ice. The continental ice sheets of the Ice Ages were more than just frozen water. They were geological agents of unimaginable power, miles-thick sheets of ice that acted like planetary bulldozers. As they advanced southward, they scoured the land clean, pushing immense hills of rocky debris before them. When this wall of ice reached the Teays Valley, it did not simply freeze the river. It completely filled the valley from rim to rim with glacial till, a chaotic mix of clay, boulders, and gravel. The river's northern path was permanently sealed, dammed shut by a plug of ice and rock hundreds of feet high. With its original course obliterated, the waters of the Teays had nowhere to go. They pooled against this new, icy barrier, creating a vast temporary lake. But water is relentless. It began to spill over the landscape, seeking any low point to escape. It found weakness in the terrain to the south and west, carving out new channels through the soft, unglaciated land. These new escape routes, forged from chaos and necessity, eventually linked up and stabilized. They became the foundational arteries of an entirely new river system, the very one we know today as the Ohio River. The ghost of the Teays is not just a historical curiosity. Its story reveals a profound truth. The ice that destroyed it was itself a product of continental forces. The slow dance of the tectonic plates had positioned the continents in a way that triggered global cooling, allowing these massive glaciers to form. So for a brief, violent epoch, ice itself became a temporary continental force, a sculptor that could erase a river valley from the map and force the birth of another in its place. The ground beneath us is not as stable as it feels. Beyond the familiar movements of the tectonic plates, a deeper, more subtle force is constantly at work, warping the very foundations of the continents. This is dynamic topography, a phenomenon driven by the slow, churning circulation of the Earth's mantle far below. Picture the mantle not as solid rock, but as a material that flows over millions of years like warm asphalt. As these massive currents of hot rock rise and fall, they push and pull on the overlying crust. This creates vast, gentle swells and sags in the landscape, so broad and gradual you could never perceive them in a human lifetime. This is not the localized, violent uplift that builds a mountain range. This is the entire continent itself, slowly breathing, rising and falling like a colossal chest. When a continent domes upward over an area spanning thousands of kilometers, it creates a new continental high point. Rivers are forced to respond. They begin to flow radially outward from this central peak, like spokes on a wheel, carving new pathways to every coast. Conversely, when a large section of a continent slowly sinks, it creates a vast, saucer-like depression in the interior. This basin becomes a giant catchment, a destination for every river in the region, potentially giving birth to an inland sea where none existed before. This deep earth process sets the stage for the most dramatic rewritings of the map. It provides the broad, regional tilt that preconditions a continent for change. While mountain ranges might block individual rivers, dynamic topography can subtly re-angle an entire subcontinent over tens of millions of years, guiding the collective flow of every waterway toward a new ocean. It is the master sculptor working in the background, using the planet's own internal heat to shape the stage upon which all other river stories are told. Deep in the heart of Africa lies a river that defies the usual rules. While most major waterways carve a path from the interior straight to the coast, the Congo River performs a vast, looping dance. It gathers water from an immense circular basin, a colossal bowl in the continent's center that collects rain from every direction. This is the Congo Basin, a continental sinkhole created by the land itself collapsing inward. For millions of years, tectonic forces have been pulling this section of the African continent apart, a process of rifting that has caused the entire basin to slowly subside. The ground itself is sinking, creating a permanent, saucer-shaped depression nearly the size of India. This relentless subsidence has forged a hydrological trap. Rivers flowing from the highlands on all sides, from the rising margins of the basin, find their escape routes cut off. They cannot flow out to the surrounding oceans because the land simply falls away beneath them, guiding every drop of water inexorably toward the lowest point in the center. The entire system is a perfect demonstration of a contained watershed, a giant bathtub with a single, powerful plug. That plug is the Congo River itself, which finally cuts a narrow, dramatic gorge through the basin's western rim to finally reach the Atlantic Ocean. The story here is not one of a river being reversed by a new mountain range. It is a story of a river born from and defined by a continental collapse, a permanent inward spiral written by the slow, sinking motion of the Earth. Australia's vast, sun-scorched interior holds a secret in its dry heart. Lake Eyre is a basin of blinding white salt, a place where water seems to be a permanent stranger. Yet this desert is the final destination for a sprawling network of rivers that flow not toward the coast but stubbornly inward, chasing the continent's lowest point. The Diamantina and Cooper Creek are not like other rivers. They are wide, braided channels that often fade into nothing, their waters swallowed by the sand long before they complete their journey. This is one of the planet's largest internal drainage systems, a hydrological island where every drop of rain that falls across a massive area is destined to evaporate back into the sky. This inward spiral is not a random quirk of geography. It is the frozen signature of a different Australia, a continent whose shape and climate have been fundamentally rewritten. Millions of years ago, the eastern highlands were far less pronounced. The land tilted gently westward, allowing rivers to make a much longer journey across a greener, wetter interior, possibly even reaching the sea. But the continent was changing. The same tectonic forces that continue to shape the planet began to slowly lift the entire eastern edge, heaving up the great dividing range like a giant, weather-blocking wall. This new mountain range did more than just create a scenic coastline. It cast a vast rain shadow over the interior, stealing the moisture from the clouds that blew in from the Pacific. The once lush plains began to dry out, transforming into the desert we see today. At the same time, this uplift steepened the land slope to the east, creating a sharp, new downhill run to the ocean. Rivers on that side of the divide, like those that would become part of the Murray-Darling system, were given a clear, fast escape to the coast. But for the rivers born on the western slopes, the story was different. Their gentle path to the sea was severed. The rising land behind them and the sinking, arid basin before them left them with only one possible direction to flow, inward. They became trapped within the confines of the Lake Eyre Basin, their flow direction permanently locked by this 1-2 punch of tectonic uplift and climatic shift. Their waters now trace the ghost of an ancient landscape, a map of a river system that has been stranded by the slow, relentless bending of a continent. Sometimes a river does not turn, it is thrown. In the dry, scarred landscape of eastern Washington state, a geological crime scene stretches for hundreds of miles. This is the channeled Scablands, a place where the earth looks like it was clawed by a giant. Deep canyons called coulees slice through the bedrock. House-sized boulders sit stranded in the middle of barren plains. This was not the work of a slow, patient river, but of a single, unimaginable event that unfolded in a matter of days. The story begins with an ice dam. During the last ice age, a colossal tongue of a glacier acted as a natural plug, blocking a river valley in what is now Montana. Behind this wall of ice, water pooled into a vast inland sea known as Glacial Lake Missoula. This was no ordinary lake. It held more water than Lake Erie and Lake Ontario combined, a towering, unstable body of water held back only by frozen fragility. Then the dam broke, the ice plug under unimaginable pressure shattered. the entire contents of the lake exploded westward in a catastrophic torrent. The flow of that single flood is estimated to have been 10 times the combined flow of every river on Earth today. This was not a flood. It was a wall of water and ice, hundreds of feet high, moving at highway speeds. It slammed into the Washington Plateau with the force of a planetary impact. The flood did not follow the existing river valleys. It ignored them. The water was so deep and so powerful that it simply overtopped the hills, scouring everything in its path down to the bare bedrock. It ripped the soil away, carved the strange, channeled landscape we see today, and left behind those immense, stranded boulders as mere pieces of gravel in its wake. This event was so violent it did not just alter the local drainage, it erased it and carved a brand new one from solid stone. Yet the stage for this catastrophe was set long before the ice ever arrived. The broad, elevated plateau that the floodwaters scoured was itself a product of ancient continental forces. Millions of years earlier, massive lava flows, driven by deep earth hotspots, had built up the layers of basalt that form the foundation of the region. This created a relatively flat, uniform platform of hard rock. When the flood came, it was this specific geology that allowed the water to behave not as a river, but as a sheet of pure destruction, peeling the land back like a scab. The ice dam provided the trigger, but the continental forces of volcanism had provided the perfect canvas. This is the ultimate lesson of the Scablands. The deep, slow movements of our planet create the terrain, the permanent setting. Then, other actors like climate and ice can step onto that stage and perform dramas of both immense slowness and shattering speed. The ground beneath our feet holds the potential for both. The Nile River carves a line of life through the world's largest desert, a testament to endurance on a continental scale. Its constancy is an illusion, the result of a 60-million-year struggle against the shifting Earth. Its story begins not in Egypt, but with a monumental heave of land far to the south. The slow, persistent uplift of the Ethiopian highlands created a massive, elevated plateau, a natural water tower that captures the seasonal monsoons. This single tectonic act provided the Nile with its lifeblood, a reliable source of water that would prove essential for its survival. But the delivery of that water to the Mediterranean was a path forged by violent change. To the east, the African continent was slowly tearing itself apart. This continental rifting, the same process that will one day split Africa in two, pried open the basin of the Red Sea. This rupture in the Earth's crust did more than just create a new sea. It warped the surrounding landscape, creating a new, northward slope that gave the ancestral Nile its initial direction, a gentle push toward the distant Mediterranean. Yet for this young river to complete its journey, it needed a stable guide. That guide was the Nubian Shield, a block of ancient, incredibly hard rock that forms the river's bedrock through much of Sudan and Egypt. While the land around it rose and fell, this geological fortress remained unyielding, providing a permanent, unchanging channel that prevented the river from being shunted sideways or captured by other systems. The Nile's path was set, a product of uplift, rifting, and remarkable stability, but its greatest challenge was yet to come. The Sahara Desert was not always a barren expanse of sand. Beneath the dunes lies the ghost of a green Africa, a landscape crisscrossed by vast networks of rivers and dotted with enormous lakes. As the climate began to dry out over millions of years, these competing river systems withered and died, their waters evaporating under the relentless sun. They became hydrological ghosts, their empty valleys waiting to steal the Nile's flow. The Nile should have suffered the same fate, its water captured by one of these ancient, low-lying basins or simply swallowed by the expanding desert. Its survival hinged on that perfect balance between its own power and the land beneath it. The river's steady flow, fed by the reliable Ethiopian rains, gave it enough erosive strength to continuously cut downward into its bed, keeping its channel lower than the surrounding, desiccated landscape. It was literally digging its own trench, a self-made moat that protected it from being pirated by the ghost rivers on either side. At the same time, the very slow, gradual tilting of North Africa, a subtle sag toward the Mediterranean, maintained just enough of a gradient to keep the water moving north. The Nile did not just passively exist. It actively fought for its life, its persistent flow and downward cutting acting as a constant defense against a continent trying to erase it. Its longevity is a rare victory, a 60-million-year demonstration of a river holding its ground against the combined forces of a changing climate and a restless continent. A river's branching path across a map is its unique signature, a design etched by the land itself. Picture the most common pattern, a dendritic network. It looks like the delicate, sprawling branches of a tree or the veins in a leaf. This familiar shape emerges when a river flows freely over a landscape of uniform resistance. The underlying rock is flat-lying and of similar hardness in all directions, offering no particular preference for the water's path. Here, gravity is the only artist. Each tiny stream finds the path of least resistance with perfect randomness, creating a network that spreads with statistical beauty. This is the pattern of a quiet continent, a stable platform where the ground has been left undisturbed for eons. But this peaceful symmetry can be shattered. When titanic forces deep within the earth begin to compress a continent, the land does not simply rise, it folds. Immense pressure crumples the rock layers like a rug pushed against a wall, creating long, parallel ridges and valleys. When a river system evolves across this new, corrugated landscape, its entire character changes. The water can no longer flow where it wishes. It is funneled, directed, and controlled by the new grain of the land. The result is a trellis pattern. In this design, major rivers carve their way along the soft, erodible rock of the long valleys, flowing parallel to the mountain ridges. Then, shorter, steeper streams tumble down the resistant ridge slopes, cutting narrow gaps through the hard rock as they flow perpendicular to the main rivers, connecting to them in a series of right-angle junctions. The map begins to look less like a tree and more like a garden trellis, a geometric grid imposed by the geology. The classic example is the ridge and valley province of the Appalachian Mountains. Those long, parallel ridges and valleys are the folded limbs of an ancient mountain chain, worn down but still dictating the flow of every waterway. The evolution from a wild, branching dendritic pattern to a disciplined, linear trellis is a direct transformation. It is a record written in water, a clear signal that immense continental forces have arrived, folding and tilting the very stage upon which the rivers dance. By learning to read these watery scripts, we can look at a simple map and see the ghost of a mountain range, the echo of a colossal collision that happened hundreds of millions of years ago. This relentless planetary churn guarantees that our current world map is merely a temporary draft. The Amazon River, having already reversed once, could very well do so again. The Andes Mountains continue their slow ascent, millimeter by millimeter, each year adding more height to that immense western wall. This persistent uplift constantly tweaks the tilt of the entire Amazon basin, altering the subtle gradients that guide every trickle of water. A future where the Amazon's flow is once more diverted, perhaps fragmenting into new inland seas or finding a completely different escape route to the Atlantic, is written into the very fabric of our active planet. Meanwhile, in the towering heights of the Himalayas, a different trigger is being loaded. climate change is not a distant threat. It is a present-day force that supercharges the engines of river piracy. As global temperatures rise, precipitation patterns are shifting. Some mountain slopes may receive torrential, unprecedented rainfall, while others dry out. Glaciers that have fed certain river headwaters for millennia are melting at an alarming rate, first increasing flow and then potentially starving the rivers altogether. This climatic chaos creates winners and losers in the hydrological arena. A river swollen by increased monsoon rains or glacial melt will gain tremendous erosive power, allowing it to cut backwards into its headwaters with newfound aggression. It could easily breach a high mountain pass and capture the headwaters of a neighboring, less fortunate river that is drying up. The result would be a sudden, dramatic reorganization of entire watersheds, redirecting the flow of billions of people who depend on them. Scientists are now using our hard-won knowledge of plate tectonics, isostatic rebound, and climate interactions to peer into this watery future. They create sophisticated models that identify the world's most vulnerable drainage divides. These are the places where the land is primed for change, where a steepening slope, a fault line, or a particularly soft layer of rock awaits the final push from a changing climate. The next great rewrite of Earth's hydrological map is not a question of if, but when and where. Our planet's story of flowing water is an unending epic, and the next chapter is being drafted right now, deep beneath our feet and high in the atmosphere. We have become the continental force. With concrete and steel, we now build our own mountains and carve our own canyons, imposing a new and immediate order upon the ancient, slow-moving dance of rivers. The construction of a massive dam is a human-scale act of river piracy, a sudden theft of a river's momentum and purpose. Where nature might take 1,000,000 years to redirect a watershed through the slow uplift of a mountain range, we accomplish a similar feat in a single generation. The Aswan Dam in Egypt did not just tame the Nile's seasonal floods, it arrested the river's very soul. For thousands of years, the Nile's annual inundation was a life-giving pulse, carrying rich, fertile silt from the volcanic highlands of Ethiopia and depositing it across the farmlands of Egypt. This sediment was the foundation of a civilization. Now that same silt settles into the still, deep waters of Lake Nasser, the vast reservoir behind the dam. The river downstream runs clear, starved of the material that once replenished the delta. The land itself is now sinking and shrinking as the waves of the Mediterranean Sea, no longer counterbalanced by the river's sediment, eat away at the coastline. We did not just change the flow of water, we altered the geological recipe of an entire region. On the other side of the world, the Three Gorges Dam on China's Yangtze River represents an intervention of almost unimaginable scale. The weight of the water held in its reservoir is so immense that it has been shown to increase seismic activity in the region, a phenomenon called reservoir-induced seismicity. We are not just building on the landscape, we are pressing down on the continental crust with such force that we are prompting the ground itself to tremble in response. The dam has also fundamentally changed the river's personality. Its flow is now meticulously regulated, its seasonal rhythms replaced by the demands of power generation and flood control. This has disrupted the delicate ecological cues that fish and other aquatic life depend on for spawning and migration. The sediment that once painted the river a distinctive muddy brown now sits trapped behind the dam wall, leading to unexpected erosion downstream that threatens the stability of bridges and riverbanks. These are not mere side effects, they are the signatures of a new geological age, one where human decisions rival the power of tectonic shifts. We have taken on the role of continental architects, but without the patient, slow testing wisdom of deep time. Every dam we build, every river we divert, is a live experiment with the planet's plumbing. We are redirecting the pathways of continents, but are we creating stable new routes, or are we simply setting the stage for a future of unforeseen consequences and hydrological surprises? The rivers that once ran backwards by the force of the earth may one day be turned again by the hand of humanity. The same forces that rewrote Earth's map have left their signature on our celestial neighbors. Mars, that cold and dusty world, is etched with the undeniable scars of ancient rivers. Vast, branching valleys snake across its surface, and colossal channels speak of catastrophic floods that once raged with a power dwarfing anything in human history. These are not subtle features, they are the bold, dry bones of a planet that was once alive with flowing water. But to understand the story they tell, we must read them with a lexicon learned right here on Earth. Our own planet's history of river piracy, continental tilting, and sudden ice dam breaks provides the essential translation guide. When we see a massive outflow channel on Mars, we recognize the ghost of a glacial Lake Missoula-style event, a titanic release of pent-up water that scoured the landscape in a geological instant. When we observe a river valley that seems to abruptly change direction or end in a vast basin, we can ask the same detective questions we ask of the Teays River or the Amazon. Was this shift caused by the volcanic uplift of a massive Tharsis volcano, tilting the entire region? Could a colossal asteroid impact have shattered the local hydrology, creating new basins and obliterating old pathways in a single, violent act? Earth has taught us that a river's path is a dialogue between the deep interior and the surface environment. By applying this hard-won wisdom, planetary scientists can piece together the climatic history of Mars from its dry riverbeds. A planet capable of sustaining complex, long-lived river systems for millions of years was a very different world, one with a thicker atmosphere, warmer temperatures, and perhaps even precipitation cycles. It moves the search for past life from a question of mere water to a question of persistent, stable habitats. The intricate channels and deltas preserved in Martian rock become potential fossil hunting grounds, not for fish bones but for microscopic clues. Earth is the only key we have to unlock these alien landscapes. Every backward-flowing river, every captured stream, and every flood-scoured plain on our own world sharpens our vision, allowing us to look at the stark beauty of another planet and see the echo of a world that was. Our oldest stories whisper of a world in flux. Across the globe, from the Epic of Gilgamesh in Mesopotamia to the tales of the Aboriginal Dreamtime, cultures separated by vast oceans share a common narrative thread, the story of a great flood that reshaped the world. Could these be mere coincidence, or are they the faint, echoing memories of actual geological catastrophes? When the last ice age ended, colossal ice sheets melted, and global sea levels rose by over 100 meters, drowning coastlines and entire continental shelves. For generations of humans living along those shores, this was not a slow, imperceptible change. It was a relentless, terrifying invasion of the sea, a loss of land that would have forced a constant, desperate retreat. The story of a world covered in water would have been a literal truth for them, a trauma passed down through countless generations, slowly morphing from history into myth. A more violent possibility lies in events like the Scablands floods, the collapse of an ice dam and the resulting cataclysm that scarred eastern Washington would have been a single, horrifying day for any witnesses. The roar of a wall of water hundreds of feet high, the ground trembling, the very shape of the known world being torn apart in hours. This is the stuff of literal nightmares. An event of such magnitude would have burned itself into the collective memory of a people, becoming a cornerstone of their oral tradition, a divine punishment or a world-ending event told and retold for thousands of years. While we can never draw a direct scientific line from a specific myth to a specific rock layer, the pattern is too compelling to ignore. These universal stories of earth-shattering change align perfectly with the kinds of planetary upheavals we know have happened. They suggest that the human mind, trying to make sense of an incomprehensible event, translated the language of geology into the language of gods and heroes. The ground beneath our feet holds one record of a dynamic planet, but the stories we tell around the fire may hold another, a cultural fossil of the day the rivers ran backwards and the world was remade. A river's new path is a creator and a destroyer on a continental scale. When the Amazon reversed its course, it did far more than simply change the destination of its water. It initiated a biological and economic lottery, determining which regions would flourish and which would fade into obscurity. The vast basin that collects its water became one of the most fertile and biodiverse places on the planet, a sprawling nursery for life built upon the rich sediments that the river scoured from the rising Andes. But for every new paradise, there is a landscape left behind. The former river delta on the Pacific side, once a lush and thriving estuary, was starved of its freshwater and sediment. It likely transformed into a more arid, less productive coastline, its ecological wealth severed by the new continental divide. The fate of entire regions was sealed not by climate alone, but by the direction a river chose to flow. This hydrological rewriting also dictates where fortune lies beneath the ground. The thick layers of sediment deposited by a reversed river are not just soil. They are time capsules of organic material, the compressed remains of ancient forests and swamps that, over millions of years, can transform into immense reserves of oil and natural gas. The very ground we walk on and the resources we extract from it are often the direct legacy of these ancient river reversals. Consider the Great Amazonian Reef, a massive coral system at the mouth of the Amazon. This reef exists precisely because of the river's reversal. The constant plume of nutrient-rich silt and fresh water flowing from the continent creates a unique, shaded environment that allows these specialized corals to thrive in deep, turbid waters where most reefs would perish. The entire ecosystem is a monument to a geological event that happened millions of years ago. From the fossil fuels that power our industries to the unique ecosystems that define a continent's identity, the invisible hand of continental forces has been allocating wealth and life for eons. The map of our world is not just a guide to places, but a ledger of deep-time geological fortunes written in water and stone. The ancient puzzle of shifting rivers is now solved with tools that see deep into the earth and far back in time. Satellites orbiting high above our heads do more than take pictures. They perform a kind of planetary weigh-in, using precise gravity measurements to detect the most subtle bulges and sags in the continental crust. These satellites can sense a landmass rising by a few millimeters each year, the slow, relentless breath of a continent still rebounding from the weight of long-vanished ice. This data reveals the live, ongoing process of dynamic topography, the vast, invisible swells that are, right now, tilting entire watersheds toward new futures. To understand the engine driving this motion, scientists listen to the planet's heartbeat. Seismology uses the energy from earthquakes, which travel through the earth like sound waves through a bell. By mapping how these waves speed up or slow down as they pass through different layers, researchers can create a three-dimensional CT scan of the planet's interior. This reveals the churning currents in the mantle, the massive, slow-moving rivers of hot rock that push and pull the crust from below, creating those broad continental swells. But what about the evidence locked in stone? Geochemistry acts as a forensic lab for geology. By analyzing the precise chemical signature of a grain of sand from the Amazon basin, scientists can match it to the unique recipe of rocks found only in the Andes. It is like finding a fingerprint at a crime scene, a definitive link that proves that specific sediment was carried from those specific mountains, confirming the direction of an ancient current. All of this raw data, from the satellite's view to the geochemist's lab, then feeds into the most powerful tool of all, advanced computer models. These are not simple animations. They are complex digital worlds that simulate millions of years of tectonic forces, climate cycles, and erosional processes in a matter of hours. Scientists can run experiments on a virtual planet, asking what happens if they push a mountain range a little higher or increase rainfall on one side of a divide. They watch as their digital rivers change course, are captured, or reverse their flow, testing their theories against the real-world evidence. This multi-pronged, high-tech approach transforms geology from a science of interpreting the past into a predictive force for understanding the future. It creates a dynamic, ever-clearer picture of our planet's restless nature, allowing us to see the continents not as static slabs, but as living, breathing entities in a constant, beautiful state of flux. This grand interplay of forces reveals a fundamental truth about our world. A river's journey is never its own isolated story. From the planet's molten heart to the peak of a mountain and the path of a raindrop, everything is connected in one continuous, dynamic loop. The immense heat left over from Earth's formation fuels churning currents in the mantle, which slowly shuffle the tectonic plates. These colossal plates collide and crumple, raising mountain ranges that act as continental dams. These new barriers force rivers to reverse their flow, carving fresh paths to the sea. In doing so, they redistribute vast quantities of rock and soil, building new land and burying old ecosystems. This relentless movement of sediment directly shapes the chemical composition of the oceans and the atmosphere, influencing global climate patterns over millions of years. That shift in climate then determines where life can thrive, guiding the course of evolution itself. The fossil of a freshwater fish, found far from its modern relatives, is not just a biological curiosity. It is the final link in a chain that leads directly back to the forces brewing deep within the planet. There is no real separation between the world below our feet and the world we inhabit. The ground we build our cities upon, the water we drink, and the air we breathe are all products of this single, integrated system. Viewing Earth through this lens changes everything. We stop seeing a collection of static landscapes like pieces on a museum shelf. Instead, we witness a single, living and breathing entity, constantly remaking itself in an endless, beautiful dance of rock, water, and life.